please all, as most of you have already done, mute your microphone. That would be perfect. So with this, Michael Spearpoint, if you are ready, then I suggest you share your screen for the presentation. Thank you.
All right, thank you. I will just get myself going. And where are we? So hopefully you can see the slide. Someone just say yes. Ruben?
Yes, it's perfect.
Cool, that's good. So as I say, Ruben says, I'm going to talk about designing experiments that can generate data for fire models. It was an interesting topic, and I'll excuse my dog barking in the background because he gets excited. Because when I first started thinking about this, I've just ended up sort of talking about how you design experiments, but there's a specific element to this about generating data for fire models. So hopefully I'll sort of focus a little bit more on that question rather than just about experiments in the widest sense. So I think the first thing to think about is, what is a model? And of course, a model is not the real world, but merely a human construct to help us better understand the real world systems. So we've got reality, whatever we're living in, and we can get philosophical about what is reality. And what we want to do is compare it to some approximation to that reality. And of course, we have different types of models. We have mathematical models, statistical models, conceptual models, and so on. So, but each of these are some sort of construct around reality. When we think about fire engineering, fire safety engineering, then these days, most people use the word model to mean a computer-based simulation tool. We talk about modeling, but of course, models might be an empirical equation, as well as what we might consider a sort of a model as we now use it. When we think about experiments, though, experiments are also not reality. I mean, they are real in the sense they're in the real world, but they're not the reality of what we're maybe designing for or what we're using eventually the model for. They're a human constructed occurrence of a physical system. So in our sort of bubble of possible models, it's like a physical analog. And so we've got to remember that the experiment we do is a sort of reality, but it's not reality as in terms of the actual fire that might happen in reality. Can I keep using the word reality? So whatever we're doing is still going to be a representation of some kind of reality. So when we think about models in terms of what we do in fire safety engineering, we might say that they can be grouped into hand calculations, spreadsheets, and then now computational tools. And of course, in ways, they're all sort of a hand calculation. A spreadsheet might be just a version of a hand calculation, and sometimes our computational tools are a collection of things that we could do as a spreadsheet or as a hand calculation. So even separating these three, they kind of meld from one to another. And then when we think about the sort of uses we put to models, then generally we might split them into fire dynamics, people movement, and structural performance. And of course, again, some models will include more than one of those things. Some will include certain elements of those. So even this sort of broad differentiation of these different types of models is only going to be broad. For the sake of today's discussion, I'm going to keep it to sort of fire dynamics, and I could use the same sort of illustration for the other two, not so much for the structural stuff because I don't do so much of the structural stuff. Talk to Ruben or something like that if you want to know more about structural fire modeling. So let's think about when we're designing some experiments for a model. Obviously, what we need to do is think about the objective. What are we trying to do? And the first question we might ask is, well, which model are we targeting our experiments towards? Is it a particular named model? So we've got a model that we want to assess for some reason with the experiments. It may be several models. We might have some reason that we want to look at some kind of comparison, or we might have some objective. We might be looking at a class of models, a group of models. It might be zone models, or it might be CFD. So that might make us think differently about the experiments we're going to design. Or we might not have any sort of specific model. We just think, well, we're going to create some experiments, and it might be just for a broad future modeling exercise. But deciding on the model might make you think about the experiments you're going to do. And then you might want to think about, well, what specifically for one or more of these models might you be looking at? Are you looking at a detailed assessment of a particular algorithm or component of a specific model? Are you looking to benchmark the wider capability of a specific model? Are you wanting to compare the performance of different models against your experiment? And you might want to also not just compare the computational capability of the model, but you might be wanting to also assess the people who use the model. And that may also get you to think about the way you're going to conduct your experiments. I'll talk a little bit about that more in a moment. But just think about what you want to do with your experiments, the model, and which aspect you might want to look at will help you or direct you in what kind of experiments you might want to do. So for example, I've sort of broken this down into, let's think about sprinkler activation and what we might want to do to model sprinkler activation. So for my first example, the objective might be to model the heat transfer in a single sprinkler. So we might have requirements. So to do that, we want to define and temperature, and therefore we might say, a wind tunnel experiment might be a good way to do this, because it gives you a reasonably precise control of the experimental conditions. So here's a wind tunnel type experiment where we were looking at the activation of a sprinkler. So that's you've got your objective, what you need to control, all the requirements, and which experiment you then choose to do that. And then you might want to model that sprinkler in whatever tool that you're interested in. So the next one might be, well, we want to model the activation where the sealing jet is generated under some defined fire conditions. So rather than our wind tunnel, which we define just the velocity and the temperature, we might want to say, well, we want the sealing jet to be generated, but by this time with a fire. So we want to get the resultant gas velocity and temperature from a fire. We might want to then say a pool fire will do that for us, because that gives us sealing jet conditions that are fairly predictable. It gives you, if you put your pool fire and you put your sprinkler in, you'll probably get a defined flow direction, and pool fires are well characterized. So you'll be able to get some idea what you might expect from a pool fire, put that into your computational tool. Does it predict what you'd expect to get from, how does it compare to your experiment, knowing you've got a pool fire with certain conditions? So here's someone who used a pool fire to do an analysis of sprinkler activation. Then we might want to try something else. We might want to say, well, we want to model the activation, but resulting from a dynamically changing fire. Rather than a nice steady state pool fire, we might want something where we get more realistic gas velocity and temperature from our fire. And so in that case, we might decide we want to use a furniture item. And a furniture item, so we get our furniture item, that will give us some kind of growing fire, but we end up with the sealing jet conditions, which are a little bit less predictable. The direction is probably fairly well defined, but our fire growth, we're going to have fire growth, and that might be a bit more complex. So when we think about modeling it, we might be wanting to not just model the sprinkler, but we now have to think about how well we might be able to model the fire growth as well, or how we're going to represent the fire growth in our modeling exercise. So here's some work was done by one of my students quite a few years, Jonathan Shelley, looking at, well, actually sprinklers and smoke detectors and heat detectors with a TV fire. And then we might say, well, we want to model the activation from a real fire. Again, the word real here, we will be careful. So we want realistic gas velocity and temperature from our fire. And now we might say, well, a real fire might consist of a number of items of furniture, which we start the fire in, then it might ignite another one, and so on. We'll get fire growth in our enclosure. And so now we have sealing jet conditions that are much less predictable. The flow direction might be less well defined, and our fire growth is much more complex. So modeling that is going to be more complicated and a lot more challenges, but it's going to be something a little bit more realistic. So here's again some work that we were doing when I was back in New Zealand, and now we've got a slightly more realistic setup where we've got several items of kind of furniture that we then allow the fire to develop. So again, it's the experiment and the modeling that we might subsequently want to do, kind of part of our thought processes in designing these various types of experiments. So we've got these four, I've got this matrix of different, I've just sort of described those. So the objectives, the requirements, and the different experiments we might do. Of course, we can get more and more complicated. So that was for a single sprinkler, but we might be interested in modeling several sprinklers, so subsequent activation of other sprinklers. So now we get even slightly more complicated in terms of what modeling we might want to try and achieve, and what type of experiment we need to set up to achieve that. So and that's kind of more realistic for the bottom three. I mean, in the wind tunnel, it doesn't really make sense. You can't even realistically do that in a wind tunnel. I suppose you could if you played around with it, but anyway. And then, of course, you can think, well, we want to be a little bit more complicated. What happens if we want to consider that after the first sprinkler activates, it also starts to suppress the fire? It also interacts with the layer, and then we add another layer of complexity to our modeling and another layer of complexity to the experiment that we're going to plan to do. So thinking about what we want to achieve, what requirements you have in terms of that experimental sort of procedure, and then which experiment might be the best for you to choose, so that you can then do your modeling assessment or your modeling, whatever you want to do subsequently. And of course, all of that then asks the question, well, which model or models, types of models, named models, are you wanting to apply these to? Is it a hand calculation, a zone model, a CFD? Is it comparing a zone model against a CFD? Is it the ability of a person to use a particular type of model? So again, the experiment that you want to do and the way you arrange it might be impacted by not just the objective of the work, but which of these tools you're wanting to use. So from there, or one of the other things to think about is then defining the experiments, how you're going to sit down and define what the experiments, some of the details of the experiments. So what measurements you're going to need to make, and therefore what sensors you're going to need to select to meet those objectives. And you might want to think about if you know which model, you have a particular model that you want to use, then you might want to think about which inputs are required by the model. Do you need to make sure that you measure those? Which inputs might be optional that you think, well, I don't need to measure that because the model doesn't, or my exercise doesn't require it. You might need to think about what the default settings are of the model, and can you change them? And do you need to take some measurements or collect some information so that when you do your modeling, you have got the right information available for you to do that modeling. The other thing, as part of the experiment, you might want to think about how you're going to process the data. You're going to collect your raw measurements from your sensors, but you might want to process that in some way. You might want to use those raw measurements to create what we call the data. So if you think about heat release rate, you will generally need to collect oxygen, and if you've got a duct, you'll need to collect temperature, and you'll need to collect velocity. So you'll need to process that into heat release data that will then you can put into your model. But it might be your model is, for some reason, you are wanting to assess its ability to take oxygen and velocity and temperature, and for it to predict heat release. So whether and how you need to process that data, you might need to think about. You might need to think about whether you're going to smooth the data or not, because often you'll end up with instrument noise. Do you want the raw data with its noise included, or a lot of the times people will smooth that data in some way, or process that data from its raw data to some kind of smooth data. And then you might need to think about how that data needs to be structured for input into the model, because there might be certain ways that the data needs to be represented so that it makes a meaningful input into the particular tool. So, for example, smoke obscuration. You might find that smoke obscuration that you measure with a sensor in one way, but the model requires smoke obscuration in a different way. So you'll need to process it so that you've got something that's kind of meaningful to put into your model. And it's quite interesting when you think about this, whoever defines a model, you'll end up with a sort of spectrum of people. So on one hand, you end up with the experimentalist, and the experimentalist appreciates the challenges of experiments, what's practical, how long it takes to set up experiments and to do all the things you need to do, what instrumentation can or can't do. So they've got an appreciation of those challenges that might need to be thought about when defining your experiments. But on the other hand, you've got the modeler, someone who's very familiar with a particular model, and they appreciate the challenges of modeling. What are the data input requirements? What is the representation of reality within the model? What computational resources do they need? And you'll find that you'll often need to, if you're sort of on one end of the spectrum or the other, to talk to this other party. So the classic one is the modeler who comes along and just wants instruments everywhere, sensors everywhere. They go, well, just put thousands of sensors in. And of course, the experimentalist will say, I can't fit them physically all in. I haven't got that number of sensors. You do realize how long it will take to calibrate them all. It's just not realistic. So there might need to be an appreciation of the two parties and what can or can't be done. The other thing is to really think about this comparison of our reality and our physical analog. So a lot of the time, I think when designing experiments is to ask kind of two questions, which again are kind of on this spectrum. How real to make the experiments, knowing that experiments aren't sort of reality as we might define it in terms of the way that a fire is real, happens by accident in some building, but also how repeatable should the experiments be, because we might want to collect up a set of repeatable experiments to give us some measure of the ability of the uncertainty in the experiments and comparing that to the uncertainty or the predictability from our model. And often these two things kind of go from one end of the spectrum to the other. So I'll try and illustrate this with a few quick slides. So for this first one is thinking about scale. What sort of scale might your experiments be? They might be right end at the left hand end being small bench scale. So we might be looking at TGA, DSC, which we can get data we can put into a model. So maybe looking at the pyrolysis model in FDS. And then we can move through to something like a cone calorimeter, sort of a bench scale again, but obviously slightly larger in scale, to a room scale, to a building scale. And of course, the building scale is more real, but you'll find that doing anything of this sort of size will be less repeatable. And so each time you'll do a building scale fire, even though you try and set things up exactly the same, you will find that they're not exactly the same. Something's going bong. I'm worried about what's gone bong. Are we okay?
We lost your slides here, Michael.
Okay, sorry. I've just my computer just let me put them back on again. Are we all right? Back on again?
Yes.
Yeah, sorry. Okay. So I realize I need to sort of just speed up. Enclosure. So the enclosure characteristics, how complicated do you make your geometry? So from on the left, a very simple room, to the middle, something a bit more realistic with a little bit more complexity, to some kind of reality. So I found this building online with all these curved surfaces, and do you do experiments in this kind of geometry, which is what real buildings might look like, to the left-hand side, which is a simple box. So the enclosure, how complicated you want to make it. And then the fuels that you use, how complicated or realistic, repeatable. So on the left-hand side, we've got a very simple furniture arrangement with just some bits of foam. In the middle, we've got some foam and a covering. To on the right-hand side, a reality, a real chair. But real chairs like this are going to be much less repeatable, but they're more real. Have a think about the expectations of the modeler. Who is going to do the modeling? Is it the people who did the experiments who are going to be doing the modeling? They'll be familiar with what happened and why. Or is it someone going to be in the far future who only has the documentation that's available? And not only that, they might not be using the model in the same setup in the model as you design the experiments for. The model itself may have changed. And that may be something that they're going to have to deal with. And also think about what sort of level of expertise you expect from the person doing the modeling. You've got the model developer who knows everything, should know everything about the model, under the engine. You've got the expert user who uses a lot, and then you've got the novice user. And each one of those, in terms of the modeler, will have different abilities, and you'll need to have different expectations on what they can or can't do. And so designing your experiments, you might need to think about who is going to be doing the modeling and what you expect them to be able to do or not be able to do. Just quickly think about the sequence of doing the experiments and doing the modeling. So a traditional method is to do the experiments, then do some modeling, and then do some sort of assessment, comparing the results. And that's probably what most people do. There's positives, you know what the experiments did, it's good for assessing the model capability. One, I think the big negatives of it is what I call confirmation bias. So people will do the modeling, not get a very good result with the model and go, oh yeah, of course, it should be really that property, or yeah, probably I should have done that. And they'll get a good result partly because they kind of know what they need to get at the end. And that can be maybe a little bit of a problem with this sort of method. A much rarer way to do it is for someone to do the modeling first and then do the experiments and then do the comparison. This has some positive and negatives as well. It also it's a better way of assessing the capability of the person doing the modeling. It can be used as a way of planning for experiments, and it does reduce what I call this confirmation bias, but it can end up with sorts of problems. If the experiments completely fail to perform as expected, then you might not be able to meaningfully compare the model to the experiments, and you might get poor comparison, which undermines the model. The other way is even rarer, is to do a sort of hybrid, do some modeling, do some experiments, do an assessment, and work this through a number of iterations. And I want to just illustrate this quickly at the end. Was a program that I was involved with back in New Zealand with my colleagues at Brands at the time, and we structured a program of small scale experiments, cone, then furniture calorimeter, then we did a single item ISO 9705 room and a multi-item 9705. And then what we did is the modeling interleaved between these various exercises. So we actually did our predictions up front, then got the cone calorimeter results and redid our modeling to look at the predictions, and then gradually we built up the information that we supplied to the modelers grew as we did more experiments. And this was really fascinating exercise. We've written up some of the work, but we've never kind of got to sat down and written it all up in quite the level of detail that I wanted to. But there is a nice YouTube video of Greg Baker who talks a bit more about the work, so there is a link there. Just wrapping up very quickly, just general consideration doing experiments is nothing to do with models, but thinking about whether you're doing repeating what someone else has done, you're doing standardized tests, or you're doing tailored experiments, how many scenarios, how many repeats, how much instrumentation, what's the capability of the laboratory that you're going to be doing the work in. And then finally, just some really practical stuff. How much money do you have? How long do you have to do it? And does that time include the modeling work as well? because the experiments might take up quite a bit of time, and then you run out of time to do the modeling. So there's just the practical thinking about how many experiments you're going to do, how complicated you're going to do them, and how much time and money do you have to get all that done. I ran a little bit, but I've now finished and I'm happy to take questions.
Thank you very much, Michael. That was a great presentation. To everybody, if you have questions, easiest thing would be to raise your hand in the chat or posting a question there. For the first questions, you can always unmute, but that can be chaotic soon. First of all, Michael, thank you very much for this presentation. Very nice. I'm happy that we were also allowed to record it, because it will be a very, very nice resource. Now, are there any questions from the audience? It's more difficult side of having online presentations. But considering we have a small time left here, oh, there's one which already arrives. So Bart Mercier is asking, where does virtual reality stand in all of this?
Yeah, that's a great question. Where does well, it clearly not real. I mean, there's virtual reality, and I suppose you might say augmented reality. Certainly, it's an interesting thing. I mean, I got involved a little bit with this sort of work with actually do with evacuation from earthquakes, and so in terms of the fire dynamics directly, you know, it's quite useful for the human behavior. I mean, there's a whole body of work that you can, I mean, you can go and talk to people like Enrico does work in this area, because in that case, you're trying to mimic reality, but the person, you're getting people involved, and they kind of know it's not real, but actually they can get very engrossed in the experiment to the point it can seem quite real to them. But clearly it's not real, because if it was real, you know, it's never real, but it's somewhere on that spectrum, and it depends what you're trying to achieve. I can't really answer it with a simple it's here or it's there. It is somewhere on that spectrum. And if I did a thing on human behavior instead of fire dynamics, we could debate that further. It's an interesting one. Can I explain more about hand calculation? I'm not sure what that question means. I mean, hand calculation, I mean a formula that you have on a piece of paper that you can put some numbers in and you get an answer. You just do it by hand on a calculator or whatever. Well, I mean, anything done as a hand calculation, we do, you know, you could do CFD on a hand calculation. If you look back to the days of in the early when they were designing nuclear weapons and that, they used to have hundreds of people sitting in a big room with mechanical calculators doing it by hand. So it's just that we're just too slow as humans to do it. I mean, you know, in theory we could all do it by hand calculation, but best of luck trying to do CFD calculation by hand. You'll do one time step in your lifetime or something.
Well, that's a very nice way to end as well. So Michael, thanks again. Very nice presentation. So if there are additional questions, everybody feel free to post them and I'll follow up, and I'll forward them also to Michael. We can return to them later. And now we actually have a second presentation coming up. And so a presentation by Kevin Smeyers. So Kevin works for FPC Risk. I've introduced it at the very start. Some people who might not have heard it. In the meantime, Kevin, you're invited to unmute and upload your presentation, share your screen. Excellent. So a presentation about heat radiation contours, as you can see, specifically industrial risk. So Kevin, if you are ready, then the floor is yours.
I hope so.
Thank you.
Yes. You can understand me? You can hear me?
Yes.
Okay, very good. Thank you, Ruben. Good evening, everybody. My name is Kevin Smeyers. I'm a former postgraduate student. I graduated in 2018. And in the meantime, I've been working for FPC Risk for 6 years by now. FPC Risk is an engineering company based in Antwerp and specialized in fire safety for almost 50 years now. It was founded in 1973. And as you can see, our projects range from conceptual fire safety to complete detailed designs for fire protection systems, both for industrial installations and for buildings and architects. Today's focus will be on heat radiation calculation. We'll use software for that, which uses some of those models Michael was just talking about, and see how we can put those models to practical use. But first, I want to point out some important differences between applied engineering, that's more our field, of course, and academic studies and engineering. Because in day-to-day engineering, we're looking for practical solutions of certain problems. And most of the times, practical actually means with regard to financial aspects. Because after all, the clients we work for are companies, and their main goal is to generate profit. So actually, we're constantly balancing between the cost of a design and a study and the level of safety that study generates. That's why when we use a model, we often need to use simplifications of that model to reduce time and costs. And of course, those simplifications should be very well chosen because we still want to have a realistic approach, or at least as realistic as possible. What that reality actually is, that's more Michael's field, I guess. So when we make those simplifications, we must make sure that the level of safety is not diminished by it. But we must make sure that we don't do, for example, a CFD calculation that takes 2 months, because our customer will not pay for that. So when we make those simplifications, we always try to make a conservative approach to be on the safe side of a possible solution. Whereas, to my opinion, an academic study is more knowledge-driven instead of economics-driven. And the approach of a realistic model is more important to get a better understanding of the topic of the study, or simply to improve the model, as it will be used in further studies. And for the people who were attending the IMFSE Introduction Day last month, you might recognize this slide, if you were paying attention, that is. This shows in general how we take on design of fire safety systems. In this specific case, this was the protection of a tank farm. So first of all, we start by gathering information on the tank farm concerning the size, the dimensions, content of the tank, used materials, combustible materials, surroundings, and so on. Using those data, we calculate heat contours, which we project on a ground plan, as shown on the right picture, as you can see. This defines a couple of scenarios, and these scenarios tells us which adjacent tanks or installations need to be protected, and legislation and standards will tell us how we should protect them. So for each scenario, we make calculations and we determine which one is the so-called worst case scenario. Once that is defined, we can design or adjust installations, water main, pump curves, etc. accordingly. But as I said, today the focus is on the calculations of the heat contours. At FPC Risk, we use a specific software for that. This is, of course, not the only one, but it's the one that we're familiar with, or at the company, I mean. And the software we use is Process Hazard Analysis Software, or Phast. I don't know where the final T comes from, actually, but sure. And Phast can be used for the analysis of certain risks, but also for the calculation and visualization of the consequences of certain events, like leaks and ruptures, pool and jet fires, explosions and dispersions like toxic vapor clouds. And they use different models for those results, or to generate those results. But since we're mostly interested in pool and jet fires, we're going to focus on the radiation model, fire and explosion. So first of all, let's take a closer look at a model that Phast uses for a jet fire. A jet fire usually occurs when a leak or rupture of a pressurized gas pipe or vessel occurs and ignites. This generates a large flame, depending on the pressure of the fuel. The flame is modeled by the program as such. It represents the flame as a conical shape, directed away from the release point, perpendicular to the pipe. So the biggest radiating surface that we see here from this conical shape is actually the mantle of the cone. It's a lot larger, whereas the flame end position is a lot smaller. Since the radiating surface defines the heat contour, the largest heat radiation contours will be radiating away from the cone, as shown in the picture below. Sideways radiation is a lot larger here than the radiation along the axis of the flame. This is somewhat different for the model of a pool fire. We use a different approach. The pool is considered a non-turbulent body of liquid. And with non-turbulent, we mean on the larger scale. If you would look at a smaller scale, you would notice a lot of temperature-driven turbulence, like Tarek talked about 3 weeks ago. But on a larger scale, you would consider this amount of liquid as being immovable. The flame on top of the pool fire is modeled as a cylindrical shape above the liquid pool, with the flame height depending on the heat release rate and the fuel, the heat release rate of the fuel, sorry, and the size of the pool. The wind effect might tilt this cylinder, as shown here on the picture, towards a certain angle. But not only that, it will also shift the base of the flame, because the base of the flame is actually the vapor right above the liquid pool. So you could see that the base of the flame is actually somewhat larger than the pool diameter itself, or the pool surface, more like. Again, the radiating body or surface is the mantle of this cylinder, and this would generate a heat contour that looks somewhat like this. We'll see some more examples of these contours later. Then, how do we use this model? It's not the idea to give you just a manual of the model, but we're going to go step by step to define a certain event. And we're going to see how we do the parameters for some of those steps. So first, in this model, you have to create what is called a study. And this can be a tank farm or an entire industrial site, including buildings. That's up to you to see in how much into detail you will go. Each of these studies contains one or more systems, like tanks, pressurized vessels, pipes, or standalone systems. And for each of these systems, we can define some scenarios. These are possible incidents, like leaks or ruptures, spills, explosions, levies, fires, and so on. One very important feature for this study is an overall parameter, is the weather conditions. These are valid for the entire site. So every incident scenario will have the same environmental conditions. And again, we try to have a somewhat conservative approach for these weather conditions. When, for example, the meteor tells us that the prevailing wind speed in a certain area is 3 meters per second for 60% of the time, but sometimes wind speeds up to 4 or 5 meters per second occur, we take 5 meters per second to be the worst case scenario. On the other hand, you do not necessarily need to take the maximum wind speed all the time. When this is, for example, in stormy conditions, wind speeds of 10 meters per second might occur, but you would expect it to rain, for example, which might have a cooling effect on the fire, and therefore it might not be the worst case scenario. In general, dry or windy weather conditions are the worst when it comes to fires. So when we take the settings, we usually take the neutral, so it's a little sunny, but with rather high winds. And we take the wind speed, generally for an inland situation, at 5 meters per second. Of course, you need to take into account the location where you are. There's a huge difference whether you're inland or at sea on an oil rig, for example. Also, it's important to have all possible wind directions. To see the impact of that, I'm going to show you these. This is the heat radiation contours of a tank fire with a wind speed of 5 meters per second. And this is the exact same fire at windless conditions. And you might see that the drawing on the left, the contours reach a lot further and actually reach down to ground level. So the impact is rather big. Sorry. Next, we define the individual systems within each study and their parameters. So we need to define the materials, possible ignition sources, and possible geometries for bunds, buildings, other industrial installations, you name it. We also have to define which contours we are specifically interested in according to which scenarios. These contours are usually defined by legislation or standards, because those legislation and standards will define when you need to take a protective action. For example, you might need to cool a neighboring tank when it falls within the 10 kilowatts contour. The one we choose mostly are standalone systems. Why? Because they're easier defined. You do not need to define the surrounding tanks or buildings, and the program does not take them into account. You just need to calculate, or it just calculates the effect of one system. In our case, we chose a vertical cylindrical tank to see what effect it has. Now we only need to choose the material stored inside the tank. Again, it's very important to choose as realistic as possible, but when this is not possible, to approach this from a conservative point of view. For example, by choosing the largest component or the component with the highest heat release rate. With a single material, it's of course very simple. It's very easy. We take the pure material and all of its physical and chemical parameters. When it concerns a mixture, we have to make a few assumptions. If the mixture is mainly one component, first line, with a small amount of other components, it's rather safe to just use the main component as pure material. So in the example of ethanol 99, we would assume 1% water in the mixture. The calculation will be made as if it was 100% ethanol. In the second boat, we have a simple mixture, but with equally large amounts of multiple components. For example, we have gasoline, which has 40% octane, 40% heptane mix with 20% of various other components. Here we might choose to consider this a complete heptane tank, which is the product with the highest heat release rate. And this would give a very conservative approach. Or we might consider this as being a 50-50 octane-heptane mixture and actually ignore the 20% of various components. those are two options. You can go for this. But when we're dealing with complex mixtures, it might be useful to actually define the entire mixture composition. Like, for example, this one. This is the composition of jet fuel A1 used in airplanes. And we see that the two main components, which is undecane and dodecane, combined together make up only somewhat half of the mixture. So it would not be advised to calculate a 50-50% mixture in this case, because some of the other components have a very high part. So for this specific case, we actually created a more or less realistic mix for jet fuel. When we create this mix, Phast calculates the physical and chemical parameters of the mixture based on the parameters and properties of each individual component. Within the program, there's also an option to add a new unknown component to the library, but you would need to define all the main properties for that, like volatility, reactivity, density, and of course the heat of combustion. Luckily, most common components are well known and are documented in the library of the program. Then we're going to look at a full surface tank fire scenario. So we have our standalone system. We chose the material we put into the system. And now we have to add an incident. Something will happen that we want to visualize. There are a few options like jet fire, ablevy, fireball, explosions. And in this specific case, we're looking for a full surface tank fire scenario. So we will choose a pool fire. We will consider the liquid level on top of the tank as being on fire. The only parameters a pool fire needs are the pool diameter, which in this case is the same as the tank diameter since it is a full surface tank fire we're considering. The program will automatically calculate the surface by assuming a circular pool fire. For this calculation, I took a 15 meters diameter for the tank. You can also add or input the elevation of the tank, which equals in this case the tank height. Because we assume this is the most conservative approach of the calculation. If the liquid level would be lower inside the tank walls would block part of the radiation. So we consider this to be a less conservative approach. In this case, I took a tank height of 20 meters. And then the contours we want to see, we define them. In this case, it's a top view and a side view. And this gives us, oh, no, sorry. First, we do the bonfire scenario, sorry. For a bonfire scenario, it's harder to define the pool surface, since the program will always assume circular pool. So you will need to define a diameter, but usually a bund is rectangular of shape. So there are actually three ways we can approach this. First of all, you could take the full surface of the bund and calculate the diameter of a circle with the same surface. This will give you, of course, a very large surface, which you can place either in the center of the bund or near the edges, depending just on how conservative you want your calculations to be. A second way is you could calculate a circumscribed circle within the bund walls. This will usually get you the largest part of the bund surface, which is an acceptable approach. The center of the fire will be the center of this circle that you defined. And we usually use this approach when we're considering medium viscous products, for which you can assume they will not fill in or fill the complete bund when there is a rupture of a tank or a large leak, because a viscous product will move and spread slower. The third method we use is an inscribed circle within the adjacent tanks. We use this when we're considering very viscous products, like, for example, asphalt, which does not flow very freely, and we can assume that the pool that it forms actually stays within the limits of the obstructions of the other tanks. This, of course, will lead to a rather small pool fire. Then, once we defined the system, the materials, and the incident you want to review, you run the model, and it generates a few results. These are basically Excel sheets, large Excel sheets filled with coordinates and radiation results. But luckily, you can also put them into graphs, and you get something like this. This one is the side view of the tank. I put in the tank, it's the gray rectangle. So we see a tank with a height of 20 meters. And you could say, you can see that the 10 kilowatt contour, which is the green line here, reaches up to 25 to 28 meters, which means that an adjacent tank with the same height placed within the bunt within 25 meters should actually be protected because the heat radiation on that tank is more than 10 kilowatts. I added some red lines, and these are the cross sections where we will actually see the footprints, which I will show you now. So we have one at 19 meters just below the burning surface, and we have one at 2 meters, which is more or less human height. So this is the footprint at 19 meters. And it shows us the horizontal reach of each tank contour at tank height. So this means that everything within the green contour at this height should be protected. This, of course, is very important for the calculation of your water demand and definition of your neighboring systems. This graph, strangely as it seems, shows the contours, the 3 kilowatts contours at 2 meter heights near ground level. As you can see, there is no 10 kilowatt contour. That contour, when we saw the cross section, it does not reach ground level. This means that for this specific scenario, piping in the bunt and product pumps near the bunt actually do not need to be protected. So this might be a reduction in costs and systems. But according to some legislations, they demand that everything within the 3 kilowatt contour cannot be used manually. So for manual intervention, everything should be placed outside the 3 kilowatt contour because it is considered to be the limit radiation that a person can endure who is wearing protective clothing. Then we're going to show the same results, but for the bunt fire. The main difference is, of course, that the pool fire is situated at ground level instead of at an elevated height. So the shape of the contours is somewhat different. Second thing we notice is that contours reach a lot further because, of course, the fire is a lot bigger. The heat impact reaches the 3 kilowatt, for example, up to 80 meters, whereas the 10 kilowatt reaches up to 60 meters. So the protection of these, or for this scenario, should be a lot larger. A lot more neighboring systems should be protected for this. In this case, every adjacent system within the range of 45 to 50 meters should actually be protected. And the manual interventions are actually limited to 80 meters outside the bunt. Practically, this means that for this scenario, you are practically forced to have fully automatic systems or remotely controlled systems, as it is impossible to approach the bunt for manual interventions. Then let's see if we still have a little bit of time, because I would try to put in a little academic experiment to see what we can do with this program. Suppose we have a pool fire with a diameter of 10 meters. This gives us a surface of 78.5, and calculated we get a 3 kilowatt contour up to 28 meters, as you can see. Now in the standalone system 2, I took the exact same pool fire, same material, same weather conditions, but we doubled the diameter of the pool fire. So this leads to a surface that is 4 times as large. And we see that the 3 kilowatt contour only reaches up to 35 meters, which is only a factor of 1.25 of a difference. If we do this again, we have a third system with a diameter of 40 meters, which leads to a surface of 1,250 square meters, which is 16 times the original surface. And yet we only see that the 3 kilowatt contour reaches up to 52 meters, which is not even twice the original. And we wonder, why is this? Well, first of all, the model that Phast uses for a pool fire, that is, has a cylindrical shape. And the radiating surface is the mantle of that cylinder. Remember the previous slides from the beginning. So the surface of the pool only has an effect on the flame height. The mantle surface is defined by the circumference, not the surface itself. So the factors times 4 times 16 are actually not that important for the actual radiating surface. Furthermore, and I don't know how this is exactly modeled within Phast, but it's something that makes sense. A larger fire will produce a lot more soot. And the flames in the middle of the pool will be partly smothered by that soot and will have a smaller contribution to the heat radiation. This also means that the pool fire will generate smaller flames than theoretically possible. And the cylinder model for the large fire is relatively to its surface smaller and has therefore a smaller heat radiation contour. That's actually our interpretation of this. It's something we've noticed when making those types of calculations. And if anyone else has any insight in that, it might be very interesting to look into. With this, I reached the end of the seminar, the end of my presentation. I hope you enjoyed it. And if there are any questions, please ask.
Thank you, Kevin. Very informative presentation. Thanks a lot. We have, let's say, limited time for a short question. If there is an immediate question, please unmute or post it in the chat. Do you see the question as well, Kevin? I can also read it out loud. Question is, how do you avoid that your client automatically chooses the cheapest safety design? Do you make your worst case less worst case?
No, usually the client will always have to follow legislation which demands the minimum. And we combine the legally minimum with usually a risk assessment of the situation. And that then we go into discussion with the client, the fire departments, governments, everybody involved. When finance becomes important, we tend to the legal minimum when making a fire safety design.
Okay, thanks. I'll take one more and then I'll officially wrap up, but you can stay online for whoever wants to, of course. Question is, how often does a fire engineer actually get involved early on in the design and construction phase?
Depends. Usually when there's a first design for either a building or an industrial site, the fire department is, just like we are, an advice organ. So at a certain time during the design, you will have contact with the fire department, you will have contact with fire safety engineers to see whether the design you are is compliant with legislation and to see if the fire department agrees with your approach. Especially when you have a performance-based design, it's very important that the fire department has a look at it and agrees with your point of view and with your possible measures that you're taking. So I would always advise include either a fire risk engineer or the fire department as soon as possible in any design project.
Thank you, Kevin. So I will take the opportunity, first of all, considering we're officially at the end of our allotted time, to thank both speakers. So Michael Spearpoint, thank you very much. Kevin Smeyers, thank you very much, both of you, for very informative presentations. To everybody, we have another seminar coming up in a couple of weeks. You will get the invites, of course, through mail and so on. The presentation of today will be available online in a couple of days. So if there are specific things you want to visit, you can do that. We are staying online a little bit more to follow up on any additional questions. And for now, I just want to thank you all for joining, and again, thank the speakers for their efforts. So have a nice evening, everybody. Bye.
Bye.